Okay. Thanks. All right. All right. So last time we talked about numeric solutions to first order differential equations. Second order differential equations are a little bit harder. So we're going to try to look at how to approach those. Hopefully my computer stops wigging out. Okay. All right. So last time we looked at a first order differential equation, how to approach this guy numerically. All right. So I took an example circuit. If you started looking at the project, the first two problems on there are first order problems, kind of similar to this one. All right, where I've got an RC like this, and I need to figure out how to try to approach this guy numerically. So I want to refresh where we were with that, and then kind of jump into the approach that we would take with second order. So this was the problem here. So I said, okay, so I'm given this right there. And I've written out what the form of the particular solution, or what the form of the total solution is. All right, now you should know this. If I have a cosine as my input, the steady state solution is going to be a cosine, right? Except we say we don't know the amplitude of the cosine and we don't know its angle. What do we always know though? If I have a cosine as my input, what do I know about the output? Always.
Frequency.
I know the frequency, right? And I know that my transient response is going to be an exponential. It's going to be a decaying exponential. So we know that, all right? And we needed to use that. What was the key thing though to be able to approach this problem? What do we have to do to be able to solve this numerically? What's the critical step?
Figuring out your time steps.
Figuring out my time steps. I need to figure out a time step. But even before I get to a time step, what do I mean, I can't solve this, right? What do I have to do to that equation? Take the derivative of what? We're doing this numerically now, right? Got to start the project. All right. My guess is probably 95% of you have not started the project, right? You got to start the project. If I want to solve this guy numerically, I don't guess solutions and stuff. If I was solving it the sort of typical sort of calculus based way, I would guess a solution. But if I'm going to solve this guy numerically, what do I have to do with this? What's that? No. I need to find y at each of the t values. Okay, so what I needed to do is I needed to basically figure out a time step. So I think Anthony said that, right? I need to get a time step, and then I need to find out the value at each of the time steps. Okay, so what we did was, what do we do with the derivative? We didn't keep dy by dt. We replaced the dy by dt, don't we? If we do this numerically, if we're asking a computer to do it, right? A computer solving numerically does not guess a solution. All right, there's no AI that's good enough to guess a solution for you like that. What is it that what am I doing? I take that dy by dt and I do what with it? What do I replace this with?
Step size.
Is it the slope part of the derivative?
Yeah, I go
definition?
back to the derivative definition, right? So I'm gonna insert a blank here. Okay, so if I take dy by dt, what's the definition of the derivative? Newton defined a derivative. What's the definition of a derivative? It's a slope at a point, right? So how do I write that?
Rise over run.
Rise over run, which in the context of a linear function, it's rise over run. But if I expand that to any function, it becomes what? What's the top part? Yeah, y of t at some point in the future minus now all over delta t. So that's a rise. Okay. In other words, from time t to time t plus delta t, how much did I rise over a delta t run? All right. And then that's not quite right. There's one more piece to it, right? Okay. Delta t is supposed to be really, really small, right? So how do I define mathematically really, really small?
The limit is t approaches 0.
Well, the limit is delta t approaches 0. The limit is that as that time step approaches 0. Right? You said that is the definition of the derivative. And from that, you can derive, okay, if I had, a t to the n power, that I can figure out that its derivative is n a t to the n minus 1. That definition is used to figure out stuff like that, to prove that stuff. But from a practical perspective, like I said, in a computers, you can have a computer solve any problem for you in the world, right? And to do that, I don't need this limit as delta t goes to 0. What do we say I do instead? dy by dt is approximately what? What can I say if delta t is small enough?
Isn't delta t the step size?
Delta t is how much I move from one time to the next. So we call it, the step size. If I let that be small enough, then basically that statement is approximately true. All right. So if I'm looking at some general function y of t, and if the time between points here, if that time is delta t right there, if I make that delta t time small enough, then the derivative can be approximated by just taking the two successive values and dividing by the time step. Okay, that's what this is saying, is I would take one value of y and the value of y next to it, subtract those and divide by the time that's passed. Right? If I had a linear function, that is rise over run, right? But for a general function, that's not necessarily rise over run. But if delta t is small enough, then this is a true statement, right? So delta t needs to be, I guess I'll say it this way. Delta t should be close to 0, but let me say delta t small enough, right? And what we spent a lot of time talking about last time is what does small enough mean, right? How do I get a good definition for small enough? Okay, so we're going to go back to that. But if I had this problem here that I had on the previous slide where I said I had, what did I have? 0.01 dy by dt plus y of t equals 4 cosine omega t, like that. How do I approach this thing numerically? How do I use this information right here to solve this numerically? What's my approach? Well, code-wise, I set up a for loop to do this, right? Basically, what I do is I say 0.01, and I substitute this expression in here. I basically say if delta t is small enough, then I'm going to let that approximately equal to become an equal to. All right, and I'm going to substitute that in there. So I'm going to say I put in here y of t plus delta t minus y of t all over delta t plus y of t equal to this 4 cosine x of t, which I'm just going to call for the moment x of t. It's my driving function. Now, that is an algebraic equation. Okay, it's purely algebraic. So what I can do is I can solve for the variables that I don't know from the ones that I do. Okay, so you guys aren't quite ready for me to just jump right into solving this, right? So if I have that expression here that I have at the bottom, what I'm doing is I say, okay, at time t equal to 0, I know that x of t equals 4 cosine omega t. And I know that y of 0, in this case, I said was equal to 10. Okay, so at t equal to 0, I can plug in 0 and see that this is equal to 4. Okay, So I had this expression here, 0.01 over delta t times y of t plus delta t minus y of t plus y of t equals x of t. So what we showed last time is I can rearrange that whole thing to basically become y of t plus delta t equals, and I called this thing right here, I called that number a, right? I said a was equal to 0.01 over delta t. All right, so I turned this whole thing into is that what I did? Hang on. All right, I called a, what did I call it? I did tau over delta t. All right, that's, this whole thing is a. If I rearrange this whole thing, it simply becomes x of t minus a times y of t plus y of t, like that. Is that right? All right. The right formula was there in the notes from last time. I'm trying to do this without doing the algebra because it's kind of a not, we don't need, you guys know how to do algebra. If I look at this here, this formula, what this is a prediction. Okay. So at time t equal to 0, I'm solving for the value of y at time 0 plus delta t. So for sake of argument, let's say delta t is equal to 1 millisecond. So 0.001 seconds. So then what am I going to do? I'm going to use this formula. I'm going to say using x at time t equal to 0, y at time t equal to 0, then I'm going to get y at 0.001. What's the next value that I'm going to get? What would be the next value I'd get? So I'd get it at time t equal 0.001, 0.002, right? So basically, instead of like in your world, right, you're used to doing calculus or whatever, and you get an answer at any time you want, right? Well, for a computer, you can't do that, right? There's infinitely many real numbers between t equal to 0 and t equal to 1 second. It's impractical to solve at all those values. I need to solve at enough values so that the answer looks correct if I look at the answer, right? That's the idea. So what I'm doing is I'm taking this continuous function, right? X of t is a continuous function, meaning it's defined at all real values of t. In reality, I can only define it at some values of t if I jump into a computer, okay? So I'm basically saying, what are the values of t I wanted to do this at? Now this, I said, is a nice little iterative formula where I can say, if I know all the values at t equal to 0, I can solve for them at 0.001. If I know all the values at 0.001, then I can solve for the output at 0.002. If I know all the values at 0.002, I can solve for the at 0.003. Okay. All right. So what we said last time is here's a piece of code that would do this. Okay. So we walked through and I said, I don't necessarily need to have the t values present in my expression. That was one of the takeaways I had last time. I didn't need the t values. What I actually said is that formula can be reduced to something where it says the next value in the output depends on the current value in the output and the current value in the input. And that's what we use. And I said, this is the perfect setup for something that I can put into a for loop. Okay. Where I basically solve for the current value using the previous value. And I just continue to do that. Last time we walked through how to do that. Now, my suggestion to you If you want to make progress on the project, I really suggest that you look at at least problem one, preferably problem one and problem two before you come to class on Wednesday. All right. Or else coming to class on Wednesday really isn't worth your time. All right. Because if you haven't started to think about the problem and I start talking, it's not going to be valuable to you. So I really do suggest that you try to do it so you know where the pain points are before you come in. All right. Some of you have, right? But I really suggest that you all try to do it before Wednesday. At least look at it to understand what the problem is. All right. So that you can kind of digest it a little bit more. All right. Because it really does get down to pretty much just utilizing code like this. All right. And so you'll serve yourself well by trying to do that. Now, the thing I said, the hard part is what? The time step. All right. You guys already kind of identified that. So how do I choose the time step? What do I have to know how to choose the time step? First of all, what's the problem? I'm trying to make sure that the output looks the way it's supposed to look. Okay. So to say that the output is supposed to look the way it's supposed to look means that I have to think about what the output's going to be I don't need to solve the whole differential equation. But if I gave you this problem right here, and I said I had this differential equation that I have right here, you know that the form of the solution is that, right? That there's two components to the solution. So if there's those two components to the solution, how do I choose a time step? What did I have to think about? I want to be able to see both of them, right? I want to see the transient response and the steady state response. All right. So there's way I talked about this last time. I said there's two features here. All right. If I've got two features, one being the transient, one being the steady state, I want to be able to see them both. Right. So I got to understand what time step will allow me to see the transient and what time step will allow me to see the steady state. And I want to make sure that I choose the one that lets me see both. Right. So the way we looked at this last time was I gave sort of a simple rule for this. And I said, all right, I need to choose it that allows me to see the smallest of the two features. Sometimes the smallest is the transient response. And smallest means like which one is the shortest, right? So what did I say if you want to see an entire exponential, how long does it take for an exponential to go through its whole lifetime? 5 time constants, 5 tau values. Okay. And that's not the entire thing, but it's basically over after 5 time constants. It's pretty close to 0. And if I want to see a cosine like this, right? If I want to see a cosine accurately, I said, well, to see that, I wanted to make sure of 2 things here. To see this guy, I need to be careful of this 5 tau thing. And what's the thing I'm trying to be careful of when I'm looking at a cosine? To see that properly, what's the timing that controls that? What allows me to see a cosine properly? What key timing thing do I have about a cosine? Frequency, or the period. From a time perspective, it's the period, right? So t equals 2 pi over omega, right? To see the exponential, I said I wanted to choose a time step delta t that was much, much less than 5 tau. Right? So I gave this definition much, much less than. Right? It means it needs to be a lot smaller than. So what I said is delta t, what's a good choice for much, much less than? What's that? Yeah, so basically, yeah, 5 tau divided by 100. You think about it, if delta t is 100 times smaller than 5 tau, then basically delta t is 1% of 5 tau, right? So we're saying 1% is small enough to be able to sort of accurately see it, all right? And then similarly with this one, I'd say, if I want to see the period, I'd said, well, delta t should be much, much less than t, or, a good choice would be that it should be t divided by 100. I could choose something smaller, right? I could do t divided by 1,000 or 5 tau divided by 1,000. But if I choose too small of a time step, this is going into a computer, right? And so I might have memory problems, right? If you're doing an embedded system, and I guarantee half of you at some point in the project are going to crash your computer because you choose a bad time step and you have a gajillion points in a vector. Or the other thing you're going to do is you're going to try to do a multiply when you meant to do a dot multiply. And you're going to end up with like a 25,000 by 25,000 matrix or something like that. And that's going to kill your computer. Okay. So we'll talk more about that as we go through some examples here. But one thing to be careful of is you can make bad choices for these things that crash your computer. All right. All right, so we basically said those are our two boundary conditions, and I want to choose the one that is the smaller of the two. Okay, so last time I gave a couple of examples with this. I said, okay, what happens if my tau is 0.001 and my omega is 2 pi over 100? And I basically split this up, and I said, okay, well, I had choice number one, which comes from my transient. All right, this came from the transient. And this over here came from steady state. And I found that, okay, to have delta t much less than 5 tau, then my delta t needed to be 5 microseconds. And to make sure I could see the steady state, I needed my delta t to be less than 100 microseconds. So which one do I choose in that case? One's 5 microseconds, one's 100 microseconds. Which one do I choose? The smaller one, right? I choose the 5 microseconds, right? And then I can see it accurately. And here I'd have to zoom in to see this, right? The transient is somewhere in here. And what I showed, and you can go back and look at that video on this. If I chose delta t equal to 100 microseconds, after a while they start to look the same. But if I look at this, my transient basically is all in one point. And if you compare these two right here, you can see that this is clearly not the same thing as the correct answer. Okay. And as we'll see with second order stuff, if I make a bad choice, I can have it do something completely different than what it actually does. I can actually, with the wrong time step with the second order system, I can actually make the transient response explode numerically rather than converge. All right. So you can make some bad choices and basically get a bad answer as a result of that. Okay. All right. So I wanted to just refresh on that. And I want to touch on second order stuff. So one of the problems I expect almost no one's kind of gotten to yet, even if you have started, maybe you did, but problem 3 on the project looks at a second order problem. Okay. And we'll talk more about that one because I suspect this is the one that's probably going to be the hardest, this problem 3. Okay. Problem 5, the very last one, is probably the easiest. All right, one little hint for you. Problem 5 is probably the easiest. Okay. Problem 3 talks about this. So it's a little bit of a what I call it a VLSI problem. So essentially, if I had a bunch of chip layout, so a digital chip, a NOT gate, right? You guys should know what a NOT gate is, right? If I put a 1 in, I get a 0 out. I put a 0 in, I get a 1 out. Okay. If you look at how that's implemented on a chip, it looks like this. Okay. Now what are these things here? I know transistors. And what is a transistor? Anybody know? Very simple device. Unfortunately, we try to make them sound like they're complicated. They're actually really easy. It's a switch.
Switch, yeah.
The switch, yeah. Right. So basically, there's 3 terminals on a switch. So if you look at a light switch has 3 terminals. 2 of them are inside the wall, right? And then one of them is the handle you have. So essentially, what you have is an electronic handle on the switch. You put a voltage on that handle, and then the switch turns on. And if you take the voltage off, then the switch turns off. And the act of turning it on, all it really does is to connect this point to this point. So when a switch is on, what's the switch look like electrically? A short circuit, right? So basically I put a voltage on this switch terminal, which more appropriately is called a gate. Right? If I put a voltage on that gate, then there is basically something that connects. You can think of a wire between this point and this point. And if there's no voltage on that gate, or specifically, if I should say there's 0 volts on that gate, what happens between this point and this point? Well, how's the switch work? It's either a short circuit in the wall or it's a what? An open circuit. This guy's basically going from open to short, open to short, open to short. Okay. So problem 3 has a long opening because it tries to sort of introduce this guy, but effectively, if I had a switch like this, if that switch was closed, then 5 volts appears right here. Yeah, if the switch is open, okay, so if the switch is open, the way this guy is set up is I've got 5 volts, resistor, and then a switch. That's the way I can think of this guy right here. Okay. So if that switch, if this switch is open like I have right here, what's the voltage right here? If that switch is open, 5 volts. Yeah. If that switch closes, you should see that it's 0, right? So basically putting a voltage here controls whether I get a 1 or a 0 out. So if you think about it, right, if I put 5 volts at this switch, at this input, then this guy turns on. So I put 5 volts in, I get 0 volts out. If I put 0 volts here on this thing, then the switch turns off and I get an open circuit. What's the voltage going to be then? Here at this point, 5 volts. So if I put 5 volts in, I get 0 volts out. If I put 0 volts in, I get 5 volts out. That's a NOT gate, right? I put a 1 in, I get a 0 out. I put a 0 in, I get a 1 out. All right, so 5 volts stands for a 1, 0 volts stands for, 5 volts stands for a 1, 0 volts stands for a 0. Okay, that's the way digital logic sort of works. Okay, and this is it's a pretty simple circuit to really understand. All right, putting 2 NOT gates together basically means if I put 5 volts here, what do I get at the output of these 2 devices? They're cascaded. If I put 5 volts in, what am I going to get at the output? 5 volts. All right, so 1 NOT gate followed by another NOT gate. That's actually pretty common to do, all right, for a couple of different reasons, all right, which I won't get into here. But this is very common for what you have in memory, for instance, or all over digital logic, right? RAM has stuff like this. So one of the things I talk about in that problem is that there's supposed to be just, if I look at a chip, there's supposed to be just a wire between this point and this point. Like on a chip, if you actually looked at it, there'd be a little copper line that would run between these 2 points. And the transistor would be made with silicon, and there'd be some copper running between the different points in the silicon. In reality, if I have a wire has some inductance to it, right? And this, for reasons we won't get into, this switch at its input looks like a capacitor. So in other words, I say looks like, in other words, electrically it acts like a capacitor. So what I end up getting is actually kind of an LC circuit. And in the problem statement, it basically says you can model this system electrically like this LRC circuit. Now, because this guy is an LRC circuit, that means you could potentially get a response that looks like that. Now, what do you guys call that? That's a second order system. And if I get that kind of behavior like I have in that picture right there, so which one is it? Underdamped. All right. Oftentimes what we'd say from a design perspective, I say that circuit rings because it acts like a bell. If I ring a bell gives me a tone, so it rings like a bell. All right. So we say that circuit's ringing. It's an underdamped response. Okay. Do you think that's desirable in a chip? It's not, right? Why would that be a bad thing, do you think, inside of a chip? Anybody know why that would be a bad thing?
Because you get a lot of noise.
You get a lot of noise, and potentially if the maximum voltage I'm supposed to have is 5 volts, what's really bad about that is that's going above the 5 volts that I have, right? And I mean, it could be, depending on how bad it is, could be 6 volts, 7 volts, 8 volts, right? That may be high enough that it causes failures inside the device. All right, so I need to make sure that's not there. All right, so in other words, typically what I need to do is to find a way to get rid of it. All right, without, this is not the purpose of this class, but you should be able to answer this. How would I make, if I didn't want that oscillation, that underdampedness to happen, how could I make it go away? Because this is the stuff we think about from you guys, where you guys are learning analysis, but as a designer, you don't ever solve differential equations. You think about the bad things in life and how to get rid of them. So in this case, I would consider this probably a bad thing. How could I make that underdampedness go away physically? What could I do to my circuit to make that underdampedness go away? More resistance, okay? If I made my R get bigger, then that would get smaller. Now, everything in life, everything in design has a trade-off. So if my R gets bigger, that underdampedness goes away, but what happens as a result of that R? There's going to be losses that come with it because R means losses. It also is going to make the transient get slower. All right. Underdamped stuff responds very fast, but very wildly, right? In other words, it shoots up very fast like this, but it overshoots. Okay. If I put a lot of resistance in there, it's going to slow down, but it's going to look like that. All right. So I don't have the wild behavior, but I also made it slower, and that might be problematic too. Okay. Because in a digital system like this, if I think about what I'm trying to do is I'm trying to get something to go. So I've got a couple of gates in series with each other, right? I need stuff to move fast through that system. So if I slow things down, that might be a problem. Okay. You know, I throw that in there. That's beyond the scope of this. I'm asking you basically to numerically solve the differential equation that comes from this. All right, but hopefully the problem is a little bit interesting, you know, in that context. The thing that's important, and I throw this in there because at the end of the day, you'll never need to solve a differential equation in your life. I shouldn't put that on YouTube. All right, Dr. Nasport is gonna be mad at me, but you're probably never going to solve a differential equation in your life. Your boss is never going to ask you that question at work. What you should know is intuitively what's going to happen when I have a second order system, and usually what are the things I need to know to be able to sort of tweak the behavior of that system, right? Well, I want it to become overdamped probably, but what are the problems with making it overdamped, and how would I make it overdamped, right? Those are the things that you need to be able to understand, and you need to understand how the math relates to the physics. All right. So anyway, that's where you're going to fit with second order stuff, is in that problem. All right, so back to our second order thing. Now I want to take my second order thing and I want to turn that into something that I can solve numerically. All right, so this is our general form where X is my input, okay? So if I'm looking at this particular system right here, how could I turn this into something? How should I try to get this numeric? What do we know? We know that dy by dt is equal to y of t plus delta t minus y of t. I said this is true if delta t is small. And I got to be careful to say small enough. And again, I said the hard part is defining what is small enough, because what's small enough in one problem is not small enough in another. All right, so we got to think about what's small enough. So what's harder now? What do I got to do now? Well, I got a second derivative, right? What do I do with the second derivative? Take the derivative of the derivative, right? So, which I could do, but it's a little tricky to put into that kind of Newtonian limit format. So let's try. I want to try something different. I want to say, what happens if I say I'm going to define another variable y2, which is equal to dy by dt. Okay. And I'm going to say I could write this thing like this: d by dt of dy by dt plus b times dy by dt plus c times y equals x. Right? All I did in going from the line above to the line below is I just broke out that the second derivative is the first derivative of the first derivative. Okay. So if I make this definition right here, y2 is equal to dy by dt, then essentially what I can now rewrite this guy and say it's dy2 by dt plus b times y2 plus c times y equal to x. All right. Now, effectively what I have here is two equations and two unknowns. Both y and y2 are unknown. And I can relate those two guys together. All right. That's the way we're going to try to approach this. I want to approach this as basically, instead of as a second order, as two first orders. Okay. That's what I've got now, is essentially two first orders. They're kind of coupled to each other, right? But they're basically two first order problems. And so the way that I set this up, and again, this is they talk about this in section 7.3 of the book, I think 7.3 or 7.4, where they talk about the similar setup. I'm just trying to be consistent with them, right? Where they say they redefine y as the variable y1, and they define y2 like I just did right there. Okay, and so that puts the whole equation into this form right there. Okay. All right. So looking at this, what I said on the previous slide, I said I've got a system of equations in this format. Okay. This is one equation. And then I have y2 of t equals dy1 by dt. So I said I got a system of two equations that somehow needs to be made numeric. Okay. This is a lot easier to make numeric, because what do we say? The general definition of a derivative, basically, right? The general definition of a derivative is what? If I look at dy1 by dt, we said that was, limit delta t goes to 0 of y of t plus delta t minus y of t all over delta t. Or we could say I could make the approximation that, right? So I'm going to call that y1. Okay. All right. Now, what else can I do? So that's one part of this whole thing, right? What else can I do? Well, I know that what's different about y2? Anything? No, there's no difference there, right? So basically y2 could be defined the same way, right? I can say it's y2 of t plus delta t minus y2 of t all over delta t. All right. So essentially what I can do is I can try to use both of these expressions. Now this guy goes in here, right? So the derivative of y1 is equal to y2. So I plug this expression for the derivative of y1 into the bottom, and I plug this guy into the top. Okay. So I plug those in there. And then I go through the process, I go through the math of trying to simplify that whole thing. So, and I'm wondering, so I'm basically just trying to do algebra in my next step. So let's just make sure we understand what's going on here. So dy2 by dt becomes y2 of t plus delta t minus y2 of t all over delta t plus by2 of t plus cy1 of t equals x of t. That's the first equation, where I substituted in the definition of the derivative for y2. And then I do the same thing here. I say y1 of t plus delta t minus y1 of t all over delta t equals y2 of t. Like that. Now, a lot of crap going on here. Right? A lot of math happening. Back to the original story. All right. What am I trying to solve for? Well, I wanted to solve for what is y of t. So back to the original expression, I wanted to find y of t. Okay. Which meant that I needed to find what we're now calling y1 of t. So if I want to do this, what am I going to do? What am I solving for here? So at t equal to 0, what do I have to know at t equal to 0? I'm solving a differential equation. What do I have to always have? Y of 0. And if it's second order, what else do I have to have? The derivative. So at t equal to 0, I have y1 of t. Right? I also have dy1, which we called y2. So I have everything. I have both y1 and y2 at t equal to 0. So if I have the value at t equal to 0, what can I solve for? If I have the value at t equal to 0, what could I solve for? So think about just one of these expressions here. You guys look at that and you're like, oh, that's a bunch of math, right? What does it mean physically? If I know the value at t equal to 0, what can I use that bottom equation that I circled? What can I use it to solve for? So if I know y2 at t equal to 0, and I know y1 at t equal to 0, I choose delta t, so I know what delta t is. What's the only thing left to solve for? Yeah, the value of y1 at delta t. And then I use the value at delta t to solve for the value at 2 delta t. And then I use the value at 2 delta t to solve for the value at 3 delta t. Right? So what we have then is I can take this whole thing right here, this bottom one here, let's just take a look at that guy. I could rearrange and see that this whole thing becomes this. The value of y1 in the future depends on the value of y2 right now and the value of y1 right now. And I could take this guy here, and if I rearrange it, I'd see that the value of y2 in the future depends on the value of y1 right now, y2 right now, and the input right now. All right, so if I solve that whole thing, basically what I would end up with is, if I rearrange it, these two expressions. I solve for y1 in the future and y2 in the future. And I can see how they relate to the values right now. So the way we set this up in code is I don't, in code, you don't have a variable that's a function of time, right? You just have a variable that's in an array. So I don't think of it like as a function of time in an array. What do we do last time? Instead of y of t, I called it what? Y of what? Yeah, y of n plus 1, meaning at the next time step, y of n plus 1 is equal to y1 of n plus delta t times y2 of n. Okay, meaning the next value is equal to some function of the current values. All right, and then similarly for this one here, I can say y2 of n plus 1 is a function of x of n minus b y2 of n minus c y1 of n all times delta t plus y2 of n. All right, I get this expression right here. So in other words, the next value of y2 depends on this whole crazy looking thing, which is a function of the current value of the input, the current value of y2, and the current value of y1. So even though it looks like a pile of equations, the physical meaning of it's actually not that hard to do. The next value depends on some function of the current values. Okay. So how would I code this? How do I get this into code? For loop or a while loop or whatever, right? But some sort of a loop would be the straightforward way to do this, right? So let's look at an example and try to think about how we would code this. All right, so I'm going to get this guy right here. Okay, so it's pretty easy for me to write the code. All right, I basically just have to go back to these formulas and get those into a loop. All right, what do I have to do before I can really write code though? What do we say? What's the critical step we identified? Yeah, delta t. Now, in this particular case, my choice for delta t is not as complicated, right? So if I looked at this guy, if I have this system right here, what does the solution look like for this? Okay, yeah. So if I talked about the full answer, I know that the total solution y of t would be a constant. I'll call it capital B, right? Where I could solve for what that is, but I don't care to solve for it. I know it's going to be a constant. All right. What does the transient response look like?
You have two exponentials with two c values.
Yeah. Ultimately, I know that I have c1 e to the s1 t plus c2 e to the s2 t. So yeah, I have two exponentials. But there's a lot of different ways those exponentials can look, right? What's the possibilities there for what those exponentials could look like? So yeah, so fundamentally what I say is there's three different choices, right? There's a range of possibilities, right? The range of possibilities, I could go from what I call undamped to underdamped to critically damped to overdamped. As I go from undamped to overdamped, what are those exponentials? How do they change? So what happens if I have an overdamped response? What are those exponentials? How do they look? They're real and they're not the same, which means that if I looked at this thing on an oscilloscope, if this was a circuit and I looked at it on the oscilloscope, it would probably look first order to me. What I would see is something going like that. All right. This is overdamp, what it looks like for the most part. And it's probably a little curvier maybe here, right? But it essentially looks first order. What happens when I'm undamped? Completely undamped. In other words, there's no resistance. So you had that guy in the last problem on the last homework. In other words, this was 0. That term didn't exist. That was the undamped case.
You just have a sinusoidal function, right?
Yep, this guy's a pure sinusoid. This guy is, he just dies. This guy here, what's underdamped do? Well, it's a sinusoid that goes away. And critically damped, I said, is kind of not all that common. He more or less looks like overdamped. Okay. Effectively, they look the same. So in other words, this guy goes from being a sine wave to being an exponential. He sort of changes what he looks like. They're all exponentials. All right. But down here, I got complex. And up here, I got real. And actually, it's going from not just complex, but if it's undamped, it's purely imaginary, roots, and all that sort of stuff. So if I really want to understand what my transient's going to look like, what do I need to know? What tells me which one of these it's going to be? What do I need to know? What's that? S1 and S2. I need to know the roots, right? So I need to get the characteristic equation. What's the characteristic equation that goes with this particular example? S squared plus 4S plus 100. Now I know when I look at this, if I do the math, right, without figuring out the roots, and I don't want to figure out the roots just yet. What is this guy? He ends up being underdamped. How do you know he's underdamped? B squared minus 4C, that's definitely less than 0, right? Which means that the square root, the thing under the square root is negative, right? That's the thing that makes this guy underdamped, okay? And there is a B term here. So there is going to be a real part to it, okay? So yeah, this guy's going to end up being underdamped, okay? The fact that he's underdamped means that I get what ultimately? What's it going to look like? What's this guy going to look like? Yeah, there would be complex conjugates. If I had to look at the transient response, this guy's going to be, let's see. If I looked at my y of t, my total solution, I said a constant plus C1 e to the S1t plus C2 e to the S2t. What does this become? Those are complex, but how do I write that? Turns into a cosine. In fact, it becomes, the way I said this was like this. 2, you can go back to the formulas there. 2 times the magnitude of whatever C1 is, e to the sigma t times cosine omega dt plus the angle of C1. Right, so there's a whole process there. I don't give a crap what C1 is. I don't give a crap what the angle of C1 is. There's a lot of hard work that goes into that. You guys suffered through that in the last homework. I don't care what C1 is. It's pretty easy for me to figure out sigma and omega d because I said S1 is sigma plus j omega d and S2 is sigma minus j omega d. Like that, right? Those are pretty easy values for me to figure out, and those are the important ones. Why am I saying those are the important ones? All right, back to what, okay, back to the big picture. What am I trying to do? Trying to solve this numerically, meaning I don't want to go through the process of figuring out C1 and C2. I want to do this the same way I would program this into a microcontroller, right? So, and you do that in problem 4 on the project. Problem 4 on the project, you're building a filter, just like you would in a microcontroller, right? And you're basically taking something that's continuous and you're basically trying to code it up. All right, so looking at this, what are the things that are important to me? If I want to figure out my time step, and that's the thing I want to figure out, what is that delta t time step? What's important here? Does this guy matter, the constant? No, that doesn't matter in this case. What about this? Well, this matters. What 2 things matter right there? There's 2 things that matter in choosing my time step. The frequency, omega d, matters, yeah, right? Because that sets the timing of what that cosine looks like, right? What about, what else matters? There's one other thing that matters, right? The response to the exponential. So in other words, how fast does this guy respond? Okay. So basically that sigma matters and that omega d matters. Okay. So if we had this problem, we're gonna go back to that, to choosing that. So if I have this problem here, all right, and I were to code this guy up and go back to my expression there, what I end up with is, if I go back to the way I quote unquote discretize the problem, I get those 2 equations which go into a for loop. Okay, so I'm going to get those 2 guys that go into a for loop, and then I have to choose effectively what's going to be my time step. So what I do is I ask MATLAB, what are the roots of these 2 things? And I get that. So these are my 2 roots, sigma plus minus j omega d. So looking at that, what's sigma and what's omega d? What are my 2 values? Yep, -2 and 9.798 radians per second. Okay. So in this case, what I did was I said, all right, technically we don't really have a time constant, but if I look at this, e to the negative sigma t, I guess I got to be careful. The way I kind of defined this is I guess that's plus sigma, the way I sort of wrote that there. All right. If I look at this, my sigma is that I can say that the exponential e to the sigma t is sort of like e to the negative t over tau. And if I had e to the negative t over tau, how long does it take for that to go away? How long does it take for that to disappear? 5 time constants. So this guy's gone in 5 time constants. So if I wanted to see whatever this guy's doing, what do I choose for my delta t? What's it have to be much, much less than? Much, much less than 5 tau. Now, what about the cosine piece here? What set the timing of the cosine? What set the timing of the cosine?
Period.
The period, right? So in this case, the period of this guy, t sub d, is equal to 2 pi over omega d, which if I do that math, that works out to be 0.6413 seconds is what that works out to be. So to see the cosine, I need delta t much, much less than what? T sub d, right? Or that the delta t has to be much, much less than that. So how did I define this whole much, much less than? I said, what's a good choice for much, much less than? Divide by 100. So I said either t sub d divided by 100 or 5 tau divided by 100. Okay. So looking at that, which one do I choose? Which one do I choose? All depends which one is which. Which one is smaller? Okay. All depends which one is smaller. So if I go through the math on this one in particular, what I'm going to see is for the delta t much, much less than 5 tau, I'm going to get the delta t should be less than 2.5 divided by 100 or 0.025 seconds. All right, this would be what I called last time choice 1. And then choice 2 here would be the delta t much, much less than whatever that period is. Delta t should be less than 0. Or much, much less than 0.6413, which says if I'd use that factor of 100, that becomes 0.0064 seconds. Which one should I choose? So one choice is something less than 0.025. One is less than 0.0064. Which one do I choose? Second one. Okay. Now, here's how I coded that. Okay. So I go in here and I got my 2 expressions. I put those 2 expressions in here like this. All right. So it's pretty straightforward. There's where they are in the loop. Right. And notice my for loop has an if statement in it. What's the if statement that I put in there? The initial condition, right? If I'm at the first point, right, I basically just copy over what my initial conditions are. And then for anything after that, then I use that formula. Okay. So then in this particular case, then I chose my delta t based on the smaller of the 2. Okay. Now make a good choice and I get that. Okay. If I actually, so I could look at that, I could look at the true solution to it. That's what it's supposed to look like. In this case, if I made a bad choice, all right, so a bad choice, in this case, if I chose delta t equal to 0.25 seconds, right, I just tried that value. What do you notice between this one and this one? Solving the same differential equation, but if I choose a bad value, what do I get? It explodes. That's not possible. Okay, that's not the true response. This can happen, right? And so I've seen people do this, in the real world, where they're trying to put some kind of a filter into an embedded system or something like that. They chose a time step wrongly, and all of a sudden you get what I would call a numeric explosion, right? Where this value should be getting smaller, but it's actually getting bigger, right? And that's going to cause problems in your code, obviously. All right, if you're using this for something. Now, in the case of problem 3 on the project, you effectively are developing sort of a little circuit simulation, right? Something that could be done in Spice. You're basically, so you guys are not Spice, you guys don't use multi-sim, right? In multi-sim could simulate that circuit for you. What you're basically doing is coding up a little multi-sim internally in MATLAB. In problem 4, you're making a filter like you could in an embedded system, okay? And you're basically trying to take some input and pass it through that filter. But both are things that are sort of common problems to have, okay? And you guys are going to work on developing those, right? So I'm going to return the exam now. Before I do that, what I'm